Okay, well, good morning, everybody. Thank you for joining Lock and Learn, a training opportunity brought to you by Johnstone Supply. So our ESCO EPA Prep Week is part of our COVID-19 relief project. And so we've been doing this now for quite a few weeks, and we're going to continue at least through the month of May. And we're going to focus the entire week this week on our EPA prep, and we have a lot of material to go over, so we're just going to jump right into it. And we're going to start on core today, so we're going to focus today and tomorrow on core. And like I said, if you have any questions, just give me a call or give me an email, and we can regroup on it later, because I probably won't be able to do any during the actual presentation. I'm going to bring my cameras down so I got a good clean view of everything. So what the ESCO Institute does is they work hand in hand with the EPA to develop an appropriate training module for being prepared for your EPA license. And this is built by ESCO, and this is owned by ESCO. It's just being presented by Johnstone Supply. And I've been talking extensively with ESCO for the last couple of weeks, and they're very excited that we're offering this one-time free opportunity for you guys. We normally do these ESCO classes once a month at each of our Johnstone Grimmie Group locations. And with the situation that we have, we're just not able to do that. So we're just going to be spending time with you and prepping you for your EPA. So if you have not taken your EPA before, or if you just have a type 1 or type 2 and you're wanting to upgrade to a universal, or even if you just want to stay up to date on the current EPA regulations, this is what you want to do, because EPA states that it is the responsibility of the technician to stay up to date on the most current regulations. So it will be your responsibility to stay updated with what is changing in our industry. And we've had a lot change in our industry. So this manual is intended to prepare technicians for the Environmental Protection Agency, the EPA Section 608 certification examination, and contains the information required to successfully complete the exam. We are not saying that if you know all this information, you're going to get a universal EPA. We're just going to give you the majority of the material that you need to know, but it will be your responsibility to prep properly for your test. All right, so let's hop into what we're talking about. So the book serves as a guide for reviewing all the materials, but it is not, if you notice what they're saying, it is not a formal refrigeration training course. So we're just covering the refrigeration fundamentals, but it is just a tool for getting the training that you will need. Technicians preparing for this exam should be familiar with the basic vapor compression refrigeration cycle, as well as common service principles, which we've covered a lot of this on our Lock and Learn series. So if you have any questions on a lot of these topics, you can go back and review some of the classes that we've already had, and we can at least give you some additional instruction on that. Never a substitute for formal training, though. So the manual's been developed with the most current information that is in our industry and what is available for publication. So, should the EPA regulations change, it is the responsibility of the technician to comply with these changes. So you have to continue your education. Section 608 of the Clean Air Act requires all persons who maintain, service, repair, or dispose of appliances containing regulated refrigerants to be certified in proper refrigerant handling techniques as required by the National Recycling and Emissions Reduction Program. And that's really what we're talking the most on, is how to appropriately remove refrigerants out of a system. So regulated refrigerants currently include chlorofluorocarbons, hydrochlorofluorocarbons, hydrofluorocarbons, and hydrofluoroolefins. Anything that falls outside of that is going to have different regulations, but we will talk about some of those, and so you have an understanding of what those regulations look like. If you maintain, service, repair, or dispose of appliance containing a regulated refrigerant, you must be certified, and this is one of the big misconceptions in our industry. If you are an apprentice working with a technician in the field, you cannot legally work under another person's certification. The only time that falls into a consideration is if you are in a classroom receiving instructor education, you can follow instructions from your instructor. But if you're in the field servicing equipment, you must be certified. You cannot work under somebody else's license. So it's your responsibility to get certified. In addition to the prep manual, the practice questions are available to help prepare you for the EPA 608, which we talked about. And you can go on that link, or you can go straight to www.escogroup.org/practice, and that will get you into those practice tests. If your exam was administered through an ESCO approved testing location, you'll be able to log into your ESCO website. So when you do register for that test, you'll actually log in and create your own profile, so you can go in and out of that training freely. You can also contact ESCO's customer service team. Here's information for them if you have any questions. If you participate in an exam that is administered in paper, which we will not be doing, you please allow 5 to 7 business days. That's the test we typically do here at Johnstone. But you'll be actually doing a live video proctored test when you take this. So as an overview, the core covers all your fundamental information of the Clean Air Act, and it's required for any one of the 4 levels of certification. So failure to pass the core means you're not going to pass any of the others. And I've actually had people spend all their time prepping for type 2 and type 3 and actually achieve above 70%, which is passing for that layer, but not pass core. If you don't pass core, you don't get anything. So make sure you're well prepared for all 4 sections, core 1, 2, and 3. If we're looking at what we're going to cover today and tomorrow, we're going to run through all of these. We're going to talk about stratospheric ozone depletion quite a bit, global warming potential. We're going to go through different dew and bubble points. We're going to talk about the different pressure systems, low, medium, high pressure, and very high pressure. We're going to go through all of our recovery, recycling, and reclaim techniques, and we'll spend quite a bit of time on each one of these. So if we talk about what each section is, so you have an understanding of what type 1, type 2, and type 3 is. Type 1 will be considered persons who maintain, service, repair, or dispose of small appliances. They must be certified as type 1 technicians. A small appliance is defined as a pre-built assembly with a factory charge of 5 pounds or less. That's a lot of different types of equipment. If we think about that, 5 pounds or less, that could be a packaged window air conditioner. That could be a refrigerator. That could be a chest freezer. That could be a water cooler. There's a lot of different things, ice machines, dehumidifiers. Those are all things that are included in type 1. So if you become a small appliance repair person, you're required to have type 1 and core. Type 2 is persons who maintain, service, repair, dispose of appliances containing more than 5 pounds of refrigerant, or if the installation requires charging. That's us. Anytime we have a system that has to be put together, where we have to calculate the refrigerant charge. Anytime we have soldering or flaring, that is type 2, and that is us. So in the residential and commercial and industrial air conditioning, that is going to be a type 2 license. So we are required to have a type 2 license in our industry, and there's quite a few technicians out there that only have a type 1. So this is a great opportunity to study for your type 2 and for your type 3. Type 3 is persons who maintain, service, repair, dispose of low pressure appliances. So that's centrifugal chillers, that's low temp, low pressure operating systems. It's a whole different classification of refrigeration, but it's still refrigeration. It's the same vapor compression cycle that we're talking about on even our fractional systems. The same refrigeration concept that is in your home refrigerator is going to be in these 100-ton centrifugal chillers. So we need to be able to understand that those are still just a large refrigeration system, but they have some special features and some special techniques that you need to know. And so that is a whole separate entity on its own. If you achieve above 70% in all 4 areas, core, type 1, type 2, and type 3, you will then be awarded a universal, and that's really the goal. We all want you to achieve your universal certification. So that is a person who maintains, service, repairs both low and high pressure as well as small appliances. So we really want you to achieve that. So the test will have 4 sections to it. So we'll have core, we'll have type 1, type 2, type 3. Each section will have 25 multiple choice questions, all pulled out of a poll of around 2,000 or so questions. So there's a variety of different tests. So the tests are randomly pulled. If you come to one of our classes and we're doing the paper one, I'm going to hold about 15 different paper manuals out in front of you. You pick which one. They're all different. A technician must achieve a minimum passing score of 70% in each group in which they are to be certified. For example, if a technician seeking universal certification, they must achieve a minimum of 70% or 18 of the 25 questions on each section, on all 4 of them. If a technician fails one or more of the sections, they may retake the failed sections without retaking those sections in which they earned the passing score. So say you go in and you pass core and you pass type 2, but you didn't get your universal, your type 3 and type 1. Well, you can go back later and just retake the ones that you did not pass. So you don't have to take the entire test over. And I have a lot of people doing that. And there'll probably be people here that are with us this week, and that's what they're here to do, is to only take the sections that they did not pass. There is one exception. Technician must achieve a passing score on the core plus 1 type. So if you go and take the test and you only receive the 70% in your core, you didn't get a type. So then you're going to have to take the whole thing over again. So study, study, study. Federal regulations require that this exam be conducted in a closed book exam by an authorized test proctor, whether it's in person or whether it is through live video. The only outside materials allowed are the TP chart and a calculator. Phones are not allowed and must be turned off and put away. Best to not allow phones in the testing room at all. I know in our classes, we've had people pull out their phones for answers before, and we typically don't pull that student out right then. We allow them to take the entire test because we're not going to disrupt the rest of the classroom. And at the end of the test, the person who's been using their phone or been using material, it gets thrown in the trash. It's that simple. If you cheat, you cheat. We don't allow it. Use of any other electronic communication device or attempts to copy, distribute, post publicly, share photos of exam questions, etc., may result in revocation of certification and will be reported to the US EPA. That has been done. I've talked to ESCO and they have verified that they have prosecuted people who have reproduced any of the test materials. Personal ID will be required, so driver's license, registered identification card, social security number, which you'll be using, and then a home or a mailing address that you'll put on that application, and that will be where your paper certificate gets mailed to. So it could be home, or it could be work, wherever you would like for that to go to. You'll need to have your date of birth, phone number, and an email address, and that will be all the information that is used to create your personal ESCO account. As required, all examination participants must be included in an online registry or look up by name, city, and state, as well as certification achieved. So there's online registry from ESCO, because if you apply for a job, which a lot of property management jobs, a lot of commercial heating and cooling and refrigeration jobs require a universal certificate. So if you apply and you say that you have a universal and you actually don't, they may call ESCO and go, hey, does John Brown have a universal? And so they can use that as verification for what level you've required or acquired. Technicians will be able to opt out of the registry by logging into the ESCO group right there. The technicians should carefully study the core and all the sections in which they are seeking to achieve a passing score. Definitely take the free online prep tests. They're right there at the escogroup.org/practice again. They are provided to give each candidate a sample of the type of questions. They're not going to be the exact questions, but it'll be a sample of similar questions. I typically spend a lot of my time going over my compression cycle in class. I'm not going to have a lot of time to go through that today, but we are going to go through the basics because it really all comes down to one philosophy. And if you can understand this philosophy, it'll make every piece of equipment you ever encounter a lot simpler. If we look at any refrigeration system, we have a low pressure side and we have a high pressure side. And we are going to have the same function of components in any refrigeration system. No matter how small or how large, we're going to have a vapor pump. It can be driven by different mechanics, but it's a vapor pump. Typically, it's driven by an electric motor. Most of the compressors we know is a vapor pump on top and it's an electric motor on bottom, or vice versa. And we're going to use that compressor to increase pressure. We're just going to pump it up. We're going to send that vapor, because remember, our compressor is a vapor pump only. We're going to send that saturated vapor that has all the heat. We're going to send it into some type of a condenser coil. It could be air coil. It could be a water coil. It could be a variety of different applications. The whole purpose of the condenser coil is to reduce the temperature of that refrigerant vapor so that it can cool back down past its dew point, so it turns back into liquid. If we have an excess amount of liquid, we can put it into a liquid receiver, and then we're going to feed our liquid into a metering device of some type. It could be a capillary tube, it could be an expansion valve, it could be a piston, it could be a variety of things. Its entire purpose is to now reduce the pressure. So we're going to take our liquid, we're going to reduce its pressure so we can make it boil. We reduce the pressure, we reduce the temperature at which it boils. As we pass through an evaporator, we're going to boil all of our liquid off into a vapor. If we have a little bit of liquid left in our vapor, we always make an extra precaution. We dump it into an accumulator, which is just a tank. So if we're working on a heat pump application or low temp application, we may have an accumulator. And sometimes on just standard air conditioning compressors, we'll have an accumulator. It's just for a reservoir so that we can make sure that no liquid gets back to our compressor. So it's really a simple circuit. It could be the exact same circuit. If we're talking about a residential refrigerator, we have the compressor on the bottom. We have the condenser on the back or the bottom. We do not have typically a receiver. We've got a capillary tube for a metering device. An evaporator coil is up in our freezer. And then we have an accumulator that's actually right next to our compressor. If we're talking about a residential air conditioning system, we're talking about a compressor outside. We're talking about our condenser coil outside that has a fan. That's an air over system. If it was a heat pump, we might have a receiver on that thing. If we get to our metering device, it could be a capillary tube, it could be a piston, it could be an expansion valve. They all do the same thing. It's just to reduce the pressure. We're going to have an evaporator coil that sits inside, and our blower fan is blowing air across it, and then we're coming back to our compressor. Simple system. If we're talking about the air conditioning system in our vehicles, we have a vapor pump that does not have an electric motor driving it. It's got what? It's got a pulley. Yeah, it's got a pulley that's being driven by our engine. And so it's just a vapor pump that's pumping our refrigerant to a condenser coil, which sits in front of our radiator, and it has our radiator cooling fans blowing air across it. It's going to go through either a piston or through an expansion valve. A lot of modern vehicles use an expansion valve. It's going to go into an evaporator coil, which is a evaporator core, which sits in front of your heater core in your dash. And we use our dash fan to blow air across it, and we're going to come back to our compressor. If it is a commercial ice machine, I've got a compressor that is going through a condenser coil, which is typically now using a tube and shell, which we'll talk about in type 3 condenser, that has city water running through it. That's going to pull the heat out of our refrigerant and send the heat down to the drain. It's going to go through a metering device, which is typically an expansion valve. It's going to go through an evaporator coil, which now is just water being pumped over the evaporator so that we can reduce the temperature of the water to where the water freezes to make ice cubes. It's the same principle that we're using in every commercial ice machine. So we don't have a fan on the evaporator coil. We don't typically have a fan on the condenser. Some of them do though. But it's just a simple refrigeration cycle. If this is a 100-ton industrial chiller providing liquid refrigerant to run commercial machinery and our air conditioning systems, it's still just got a great big compressor outside. It's got a big condenser coil outside that's got a bunch of fans. If it was a big cooling tower, it's actually got water pumping over it. You've seen, you know, the steam coming out of those kind of condensers. That's all it is just a condenser coil. It's blowing air and it's removing the heat out of the water. It's going to go back into some kind of a metering device, into some kind of evaporator core, whether it's air conditioning system or refrigeration system. You can run all sorts of stuff. Same philosophy. So don't get confused by the size of equipment. It's still going to be the same vapor compression cycle. And it doesn't matter what refrigerant is in it. We use different refrigerants because of their characteristics, but they all do the exact same thing. I could spend probably 2 hours just on this, and we have a lot. If you go back to like our superheat and subcooling courses that we did on YouTube, we really dive into that. Brian does a great job talking about superheat and subcool. So if you want a review on that, go back to our YouTube channel and you can follow through that stuff. So there's different types of compressors. If you look at those, every compressor is going to have a low side valve and a high side valve. It's going to bring in a low pressure vapor and it's going to pump it up to a high pressure vapor. The 3 stages inside of a condenser coil, no matter what condenser coil it is, remember, same philosophy. It's going to come in with superheated vapor. As it passes through there, it's going to start turning back into liquid droplets. By the time we get to the end of it, we should be all liquid. And by the time we get to all liquid, we're actually going to cool it just a little bit more to make sure that it is completely liquid with no vapor in it. And that is going to be a subcooled liquid now. Same liquid, it's just a little bit cooler. It's not changed state, it changed state in the condenser. It's just a cool liquid. Our metering devices are all doing the exact same thing. It's just reducing that pressure. We're coming in with a high pressure liquid, high pressure subcooled liquid, and we're coming out with a low pressure liquid. It's not a vapor, it's a liquid. It has vapor in it, but it's still about 75% liquid and 25% vapor. That vapor is what we call the flash gas, but it is primarily liquid at this point. It's just a lower pressure liquid. But whether it's a capillary tube or a fixed orifice or a expansion valve, all doing the exact same thing. If we look at an evaporator, you know, what we're doing in an evaporator coil, all of them, every type we run into, we're going to take that mixture, that 75% liquid, 25% vapor mixture. We're going to go into the evaporator. It's going to boil on its own. It doesn't need any assistance from us. We reduce the pressure, which caused it to start boiling. So we don't need to move air across it, but we're going to go ahead and take advantage of that process and try to remove some of the heat from our space, or remove some of the heat from our water that's passing over on a commercial ice machine. So we're going to pass through that system. All of our energy is exchanged while we are boiling from a liquid to a vapor, right? So by the time we get to the end of our evaporator coil, it should all be boiled off. There should be no more liquid. And so we just want to make sure there's no liquid, because the next stage of our system is our compressor, which is a vapor pump. So we want to make sure we've boiled off. So we know that we stopped boiling around here. We just let that temperature rise a few more degrees, so that by the time it gets to the outlet, it is considered superheated, which just means it's heated above its boiling point. You know, if that was water at room temperature, water boils typically at what, 212 or so? So if I measured some steam and it was 215 degrees, I would say that, oh, it superheated by 3 degrees. That's all we're doing. We're not changing its state once we turn to vapor. We're there. We're just going to heat it a little bit more, just to make sure that there is no liquid getting back to our compressor. Liquid gets to our compressor, it's going to destroy our vapor pump, or it's going to destroy the bearings in our motor. All right, a system that uses a thermostatic expansion valve, or TEV, is usually equipped with a receiver located on the liquid line directly following the condenser, because remember, that expansion valve is expanding. It's moving, it's changing the flow of refrigerant. So if our compressor is just pumping along, but our coil says, hey, I don't need that much volume right now, I'm going to go ahead and use my expansion valve, and I'm going to pinch down a little bit. Well, then that backs up how much liquid we have in our system. So we store it in a receiver. That's all it is, just a tank to store excess. An accumulator, when used, is located on the suction side. So accumulators prevent any liquid that might flow from the evaporator to get into that compressor. Remember, we cannot get it in there. We have service valves in our equipment. We have typically a couple different styles of service valves, depending on whether it's unitary air conditioning or it's on commercial refrigeration. So if we look at the position of most of those, if we were looking at this is more common on the commercial refrigeration system. So with those, if you walk up to a commercial refrigeration system, you put your gauges on it, you're actually not going to have pressure, right? Because if you walk up to a residential air conditioning system and you put your low loss fitting on here with your hose, you're going to be able to read your pressure. Well, it's a different style stem on commercial refrigeration. Commercial refrigeration is actually going to use what is called a back-seated service valve. You walk up to a commercial refrigeration piece of equipment and you put your gauges on there with your low loss fitting, you're not going to read any pressure. We also use some of these every once in a while in commercial air conditioning. So if you walk up to a system, don't assume that there's no pressure in there. Make sure what type of valve, because this valve has a cap on it. It typically has a hexagonal shaped fitting, and then it has a long, elongated stem cap or stem cover. If you see that style of cap, because remember, if you're talking about a residential typically has a hexagonal cover, but it's just a cover, right? It's just a flat topped cover. If you have an elongated stem on your cap, that means you have a long stem service valve, and it's probably a back-seated style. So you actually have to take your service wrench, and this has got a square tip on the end of it. You take your service wrench and you run that in, just even a quarter of a turn is sufficient. So be aware that we have a couple different styles of service valves in our industry. How to use a PT chart, because not everybody understands a PT chart. So what does a PT chart actually do? It provides the pressure temperature relationship of refrigerants. So if we take it at its core essence, what it is doing is telling us at the pressure that is in our system, it's telling us what temperature our refrigerant is going to boil or condense. So we can manipulate boiling points. I do this in one of my classes. When I'm doing this PT chart, I actually take a mason jar of water, I put it on a desk and go, hey, what temperature does water boil at? If you don't know, you need to come back and watch some of our flex train classes, because we actually talk about that. Because water is a refrigerant. It changes state. It changes from a liquid to a vapor, changes from a vapor to liquid. It also changes from a liquid to a solid. So we're just manipulating in the same way with refrigerants. So whether the tank is half full or has just a few ounces of liquid, the pressure will be the same if both tanks are at the same temperature. So the refrigerant is going to have a stable state in it, and we actually show this in our classes as well. I can tell what refrigerant is in a tank by letting it stabilize. So if I leave it in a room that is 72 degrees overnight and I come back the next morning, it's still 72, I know that my refrigerant is stabilized at 72 degrees. I can take my temperature pressure chart and go, hey, R410A at 72 degrees is X. If I go R410A and it's an 80 degree room, R410A at 80 degrees, I can put my gauges on there and I'll have 236 PSI. So it's a relationship to our temperature and our pressure. Refrigerant will migrate to a compressor's crankcase and mix with oil when there's a difference between the oil pressure and the refrigerant vapor pressure. Compressor crankcase heater is used to control that. So a crankcase heater is absolutely crucial on the operating of a system. If you have a crankcase heater, particularly on heat pumps, you need to verify the condition of that crankcase heater, because it's used to keep that oil hot so our refrigerant doesn't migrate back into it. Remember, we don't want liquid into our compressor. An oil sample should be taken when the unit has had a leak or a major component failure, because we're going to be looking for contamination or acids in the system. Refrigerant oil samples are also taken when moisture, acid, or oil sludge formation, oil waxing, or residual acidic oil from a burnout are suspected problems. That's how we can tell what happened to the oil in the system. Finding and repairing leaks in the system will conserve refrigerant when servicing an appliance. So flushing filled tubing with liquid refrigerant to clean the tubing after burnout is not recommended. It is actually against the law. We have specialty cleansing. They're basically our refrigerants. They're a boiling liquid, but they're not a chlorine or fluorine-based refrigerant. They're a solution, a cleaning solution. We use a lot of like R11X flush. So we don't use refrigerant to flush out a line set. We use certified cleaners. After we make a major repair, the appliance should be dehydrated by evacuating the system to a minimum of 500 microns. Every manufacturer has a requirement of 500 microns. I actually see people that are routinely running them down to 250 just to verify that they have gotten even below the manufacturer's recommendation. If you get them down to that point, you know that you're going to have a nice dry system. And we've actually got videos on how to properly evacuate a system and do it quickly and efficiently. Under no circumstances should a hermetic compressor be operated when there is a vacuum in the system. Electrical arcing can occur that will burn the terminals inside of the compressor. So we have to make sure that our electrical disconnect is off when we're pulling vacuum on our systems. When we talk about the gauge manifold set, I always teach in my classes how to read superheat and subcooling, actually calculate superheat and subcooling using a gauge manifold set, because they are a little bit different if you look at those. And it's the most important tool in our industry to be able to understand the pressures inside of a system. There's a low side and there's a high side, and depending on the refrigerant, the high pressure gauge may be rated 500 if it's an R22 system, sometimes even lower than that, and 800 if it's an R410A or higher. Now, the compound gauge measures system pressure for low side in pounds per square inch, PSIG, and vacuum in inches of mercury. This is what makes the low side gauge different than the high side gauge. The high side gauge is just all positive pressure. The low side gauge is not really a low side gauge. It's called a compound gauge because it reads negative pressure in vacuum in inches of mercury, and it reads positive pressure in PSIG. One of the things that I always point out to people, because they don't always understand what our internal hashtags are. Remember, we're talking about our temperature pressure chart. If I had a paper temperature pressure chart, that is telling us at what temperature our refrigerant is boiling based on the pressure in the system. That's all these inside dials are. We've just taken that PT chart and put it on a gauge. So if I put my gauge on and I have 60 PSI on my system, then I know at what temperatures my refrigerants would boil. If I had, this is R22 on the green dial, my R22 would start boiling at around 33, 34 degrees, right? So anything above 33, 34, I would be vapor. Anything below 33, 34, I'm gonna be liquid. If I was an R410A system, I would have my refrigerant boiling off at around 22 degrees. If I was an R134A system, my refrigerant would be boiling off at around 62-ish, somewhere in that ballpoint. So all we have actually done is taking our fold-out temperature pressure chart and we've put it onto our dials so that it's easy to see. So I always teach people how to use these mechanical gauges before they go to an electronic set. I love electronic manifold gauges, but if you don't understand what they are calculating, you're not doing yourself any justice. If you don't know what we're talking about here, I highly recommend, I encourage you to spend some more time understanding superheat and subcooling. So there's your high side gauge. It's all positive, no negative pressure on it whatsoever. An electronic manifold may have combined temperature probes to measure those temperatures so it can calculate superheat and subcooling. And I love using electronic gauges. They do the job for us faster. But like I said, if you don't know what they're doing, don't fool yourself. Don't look at a number and judge a system by the number that you're being told. Understand what that number is. Go back to our superheat and subcooling class. EPA recommends that hoses be equipped with low-loss fittings or valves that manually close or which close automatically to minimize refrigerant loss when they are disconnected. There's a name for this, and you'll probably encounter this if you're taking a EPA-regulated test of any type. Minor releases when connecting or disconnecting the hoses for servicing and recovery are considered to be a de minimis release. The minimum, de minimis. This type of release is not considered unlawful. So by law, you have to have fittings on your hoses. If you're just using standard hoses that are open on the end without any type of a low loss fitting, and you connect those onto an air conditioning or refrigeration system to service it, and you take that off and all of that refrigerant is escaping out of your hose, you're actually breaking the law. So something to be aware of. We need to make sure that it has fittings to make it a de minimis release. The gauge manifold and hoses must be pressure rated to handle the refrigerant that's being used. If you go to a yard sale and pick you up an old set of R12, R22 manifold gauges, you're not going to want to put that on that R410A system. The hoses are probably not rated for burst pressure properly. So be aware that your hoses need to be of proper ratings. Now, when we get into the science of why we're here, the main topic is going to be stratospheric ozone depletion. That's the whole reason the EPA is in our industry. You know, EPA is governing what we do because of effects that we have found in our ozone. And it primarily happens with our stratospheric ozone depletion. There's going to be a lot of science here. So if you're science buffs, you're going to enjoy this. If you don't like science, you may struggle on understanding some of this. And you need to understand what we're talking about. So this would be really, really good stuff to do prep courses on if any of this is unfamiliar to you. So let's just kind of rebrief of what we're going to be talking about. So stratospheric ozone helps form the Earth's protective shield. The ozone layer protects Earth from ultraviolet radiation from the sun. And we know that if you're from my generation and older, you're going to know the word the ozone hole. You've been told about the ozone hole. A lot of younger generations weren't focused as much on the ozone hole. We're going to talk about that here in just a minute. But through the 1990s particularly, we started talking about this thing called the ozone hole and the hole in the ozone layer. And we talked about it in school, and we started understanding that we had this hole in our ozone, and we didn't really dive into what it was. We just knew that it was there, and we knew that it had some negative effects. Well, what that is, when we start talking about the ozone layer and the hole in the ozone, we need to understand where it's coming from. And what we're talking about is we're going to talk about stratospheric ozone depletion. So the stratosphere is a layer of vapors that is between 7 and 30 miles off from Earth's surface. Very important to know, between 7 and 30 miles. And ozone depletion potential is, it measures the ability of a substance to destroy ozone in the stratosphere. So what scientists found in the 1990s when we started recognizing what this hole of the ozone is, and what it really is it's the hole is considered to be, when we think about it, we just think about like something just burst through and burnt this hole into the stratosphere. Well, it's not really that. It's really a large area of the stratosphere where we have measured a depletion of ozone quantity in that area, and it's a very significant area. But we were measuring it, and we noticed it increasing. We noticed this hole growing, and we didn't really know why. So we started looking at why the ozone was depleting. So we started measuring different chemicals that were found in the stratosphere over a period of time. And then we started looking at what things could be the potential ozone depleting substances, right? So we started looking at that. And we were also finding that as the ozone layer the hole in the ozone, or this depletion of ozone, was increasing, so we noticed some effects around the world, and we noticed that it was a global problem that was affecting all of us. So we needed to find out what was going on, why we were having this issue. So one of the most serious results from the thinning and damaging of the stratospheric ozone layer is an increase in the rates of skin cancer in humans. And I'm here to preach this to you. I mean, I lost my father just not even 2 months ago from skin cancer. He worked heavy machinery through the 1980s, 1990s, and 2000s, before they started using canopies, before they started understanding the severity of skin cancers. And we are really finding a huge increase in the amount of skin cancer in humans over the last 3 decades. And we're finding that it's very much because of the destruction of our ozone. All these little spots on my face, every few months I have to get them burnt, and that is because of working in the HVAC and refrigeration industry, being on roofs all the time, being out in yards all the time. It is, as technicians, we need to be very aware that we are working and living in the environment that has become more dangerous over time. So we started looking at what was going on, why we were having these increases in skin cancers, why we were having these increases in cases of cataracts around the world. And so we really started finding that it was an effect of our environment, even our crop yields and marine organisms. We've all seen, coral reef, destructions and devastation, and it's all happened in a very short window of time, right? So we knew that this hole in the ozone was probably a culprit of all of these other things that we were finding. So we started looking for that, and we started measuring higher levels of chlorine and fluorine. So scientists started going, okay, well, are there other places where we can get this? And we did. We would find that air samples taken over erupting volcanoes showed a increase in chlorine that would be up in our stratosphere. And we're like, oh, well, maybe it's volcanic eruptions. Well, then we'd start seeing that the particular type of chlorine that was being released by volcanoes would actually return back to the surface the way nature intended it to, right? But then we started finding that there was a lot of chlorine and fluorine that was staying there. And as we started measuring this increase of chlorine and fluorine in the stratosphere, we started noticing that it was a direct correlation to the chlorine and fluorine that we were manufacturing down here at the crust, at the surface. So we found that the rise in chlorine measured in the stratosphere matched the rise in the amount of fluorine. They were going up the same. And they were a very different chemical formulation than the chlorine that was coming from the volcanoes. And we noticed that this increase of chlorine and increase of fluorine were following each other. They were following a path. So the rise in the amount of chlorine measured by NASA and other agencies, and that were measuring it in the stratosphere over the past 20, it's almost 30 years now, matched the rise in chlorofluorocarbon and hydrochlorofluorocarbon emissions over the same time. So as they were tracking refrigerant use and refrigerant release, they went, uh-oh, we've got a problem. These refrigerants are our culprit. We talk about global warming a lot now, but in the 90s, we talked about the hole in the ozone because that's when we found the direct correlation. Yes, carbon fuel emissions are a major component to global warming. They don't have much to do with this ozone depletion factor. And so what we found, and it was very, very clear, that the culprit was chlorine, man-made chlorine. That chlorine-containing refrigerants have changed the natural balance and thus depleted a significant part of our ozone layer. And we went, holy smokes. Let's study this a little bit further and let's find out what's going on. So what they found was that if we look at an ozone molecule itself, so an ozone molecule in its essence is a component that has 3 oxygen atoms, all tightly bonded to each other, right? That's it. It's oxygen, oxygen, oxygen. But they molecularly connect and they form a very, very tight bond. And by design, that's what they're constructed to do. That's what they were created for. And what they do by having that bond is that they reject ultraviolet radiation. So what we did, and we were able to prove this in labs, we've seen it going on in the stratosphere, but we're able to prove this in labs, we would find that when we introduced a chlorofluorocarbon molecule with ultraviolet radiation, we could simply take a UV light and we can take a vapor refrigerant and we can penetrate that with UV light. And what would happen when ultraviolet radiation came in contact with a refrigerant module, and this is chlorofluorocarbons, we're talking like R12, ultraviolet radiation would separate off one of those chlorine molecules or multiple of those chlorine molecules. Then when you had that free chlorine molecule could actually introduce itself with the ozone molecule, and it had a molecular weight that would draw off one of those oxygen molecules, oxygen atoms. So we no longer had an ozone molecule that had 3 oxygen atoms. We would actually tear it apart with one of our chlorine atoms. So our chlorine would bond with the ozone molecule, pull off one of the oxygen atoms, and now we were left with 2 new unique chemicals, a chlorine monoxide and a diatomic oxygen, O2. O2 is not a big deal, right? O2 is pretty good stuff. The downfall is it didn't have that molecular tension that it used to have when it was an ozone molecule to reject ultraviolet radiation. So now we have 2 new chemicals floating through the stratosphere, chlorine monoxide and a diatomic oxygen, and we were able to measure those. We were to measured an increase in chlorine monoxide, measured an increase of diatomic oxygen, measured a decrease in ozone, and unfortunately, the ultraviolet radiation started penetrating through. All because of a man-made chlorine molecule. So the chlorine monoxide, well, it will collide with other ozone molecules, releasing its oxygen atoms and forming 2 O2 molecules and leaving the chlorine free to attack another one. So it used that chlorine molecule to destroy an ozone, became a diatomic oxygen and a chlorine monoxide, and then pulled that chlorine off and began that process over again. So a single chlorine atom can last in the stratosphere for 120 years. And while it is there, it can destroy up to 100,000 ozone molecules. That's pretty significant. So if you think about that, if I take 1 pound of a chlorofluorocarbon, I can potentially destroy 100,000 pounds of ozone molecules. That's huge. When we started seeing those numbers, we immediately had to make a worldwide stance to change things. So the chlorine in our chlorofluorocarbons and hydrochlorofluorocarbons, they neither dissolve in water nor break down into compounds that dissolve in water. So it doesn't just rain out of the atmosphere. If we look at natural chlorine, naturally occurring chlorine will dissolve in water and rain back out of the stratosphere. It doesn't stay up there for 120 years. So hydrofluorocarbons are made up of hydrogen, fluorine, and carbon, right? So all the HFCs that we work with, hydrogen, fluorine, and carbon, they do not contain chlorine that affect the ozone layer, but most hydrofluorocarbons have a high global warming potential. So what we found was, and we're going to dive into that a little bit further. So in the 1990s, we started going, hole in the ozone's from the chlorine. Oh boy, we got to get rid of some chlorine. So we started re-engineering our refrigerants and we started removing the chlorine out of them. What we ended up with now was hydrofluorocarbons, right? So with hydrofluorocarbons, we had no chlorine, but we had a fair amount of fluorine in them. And so what we started seeing was, as the ozone layer started repairing itself, which it has been, the ozone layer has been repairing itself very significantly for the last 3 generations. But then we started noticing the Earth is still warming, and we went, oh man, what happened? Thought we got rid of that when we got rid of the chlorine. Well, what we found was that we had another scenario that we didn't even look at when we were doing all of our studies in the 1990s. We weren't looking at that global warming effect of the gases. What we found was fluorine was an additional culprit. So when we're talking about ozone depletion, we're talking about chlorine. We're talking about global warming potential, we're talking about fluorine. So global warming potential was established to provide comparisons of the global warming impacts of different gases over a span of time. So they had to have something to compare all of this against, right? Even our chlorine refrigerants and our fluorine refrigerants, we had to have something to base it, because I could say, hey, that kid's bad. Well, who are we comparing that kid to, right? We have to have a standard to be able to measure things. So we found CO2 to be that we're going to measure. And so we measure all of our refrigerants today based off from the effects of CO2. So all of our numbers are going to be comparative to CO2. So CO2 is used as a baseline measurement for global warming potential, and it's going to have a base value of 1. There is another refrigerant out there that has a 0, and we'll talk about that in a little bit, but we don't want to use it. So CO2, if any of you are familiar with Don Gillis and the good people over at Emerson, we're seeing CO2 is going to be a refrigerant that's going to be widely used, and we're going to dive into why CO2 is being used as a base. All right, so let's talk about some global warming potential real quick. So most hydrofluorocarbons, HFC refrigerants, such as R410A, we all know that one, they have high global warming potentials, sometimes thousands of times greater than CO2. So a hydrocarbon and hydrofluoroolefins, HFO, they have the lowest global warming because they have the low amounts of fluorine, right? So we really have got to reduce the chlorine and we got to reduce the fluorine no matter what. If we look at the global warming potential of some of these new refrigerants like R600 and R290, which is purified propane, and R441, they are significantly lower when compared to the GWPs, or global warming potential, of the HFC refrigerants such as 134A, 407, 404, and 410A. We know those refrigerants, right? 134A in vehicles. It's in light refrigeration equipment and commercial refrigeration equipment. We know 40C is a replacement R22 style refrigerant. We 404 is our commercial low temp refrigerant, and R410A. All of these are on the way out. They're all on chopping block. We're going to dive into why very quickly. So with non-ozone depleting and very low global warming potential characteristics, hydrofluoroolefin or HFO refrigerants are a good fit for the HVACR equipment. So you're going to be seeing a lot more of these HFO refrigerants. Most HFCs have very high global warming potentials, a characteristic that makes them damaging to the environment. R410A, the main one right now. So refrigerants may be identified by their type, whether it's all about what chemicals are inside of them. Those CFCs, chlorofluorocarbon, chlorine, fluorine, carbon, that's all it is. Hydrogen, fluorine, chlorine, and carbon. And the American Society of Heating, Refrigeration, and Air Conditioning Engineers, or ASHRAE, number, they have the R plus the ASHRAE number, such as 134. It's all the chemical configuration. So that's what we're using our designations for. We have to start talking about classifications of refrigerants, and we're going to have a little bit of this in probably every section of this prep. So when we look at refrigerants, we're going to have a new classification chart, and this is going to be very important because this classification chart is going to be used for a variety of applications, because now we're talking about flammable refrigerants, right? So now we're going to start getting like the DOT and other different federal jurisdictions involved with the handling of our refrigerants, because in the past we've not had flammable refrigerants. We're going to have flammable refrigerants going forward. So you need to understand this classification, and you need to understand it very well. If we look at the classifications, it's going to have a letter. It's going to begin with a letter. If it has a low toxicity, it's going to have an A. If it has a higher toxicity to it, it's going to have a B. So that's going to get it into a classification. Then we're going to, based on its toxicity, how poisonous it is. And then we're going to talk about how flammable it is. And we're going to go, right now, we're going to go from 1 to 3. So if it has very low flammability, it's going to get a 1. If it is very flammable, like propane or butane, which are very, very flammable, it's going to get a 3. If it is a low flammability, it's probably going to get a 2, or a slight flammability. And this, when they say slight, they mean it will not maintain its own combustion. When Paul was doing our class on combustion analysis, we're talking about the trifecta for flames. We're talking about we need to have a source of fuel, we need a source of oxygen, and a source of ignition, or heat source, right? Well, with an A3 or with a 3 or a 2, once you light those, they will maintain, they will stay lit on their own. When we get into an A2L, they will not light unless they have a continual ignition source. They have to have a constant flame for those to have any type of flame off of them whatsoever. So they cannot maintain their own combustion cycle, basically. And it's very important to know, because A2Ls are going to be a classification that is going to take over our industry because it is low global warming and low or to no ozone depleting. So we need to know that chart very, very, very well. Come back and get familiar with that chart. Hint, hint. CFC refrigerants, they have the highest ozone depleting potential and are the most harmful to stratospheric ozone. So we found that out. That was found in the 90s. CFC refrigerants contain chlorine, fluorine, and carbon. So chlorine is the component that poses the biggest threat to the ozone. So that was like our R11s and our R12s. So we did a quick job of cutting those out of our system. We'll talk about that again here in a minute. Hydrochlorofluorocarbons, HCFC refrigerants, they contain hydrogen, chlorine, fluorine, and carbon. The hydrogen makes them a little less harmful to the stratospheric ozone when compared to CFCs, but it's the fluorine that really does most of our damage. So the hydrochlorofluorocarbon refrigerants that have an ozone depletion potential of more than 0, they range between 0 and 1. Those are going to be like HCFC, R22, and R123. So we're going to talk about those a little bit further. If we talk about HFC refrigerants, those are refrigerants that contain hydrogen, fluorine, and carbon atoms, right? They don't have the chlorine. They have the lowest or no ozone depleting potential, but they do have an effect on global warming because of the fluorine. So that would be like our 134s, our R410A, our 404, 407, 422B. You know, pretty common refrigerants to most of us, especially in the residential HVAC and light commercial world. That's our common refrigerants. We're going to see more HFOs, or hydrofluoroolefins. They contain hydrogen, fluorine, and carbon with at least one double bonded molecule. So they have multiple carbon cores to them. So they're a more complex structure. HFOs have no ozone depleting potential because there's no chlorine in them, but they do have a small effect on global warming because they have a little bit of fluorine in them. So it's all about working with the ozone depleting and the global warming, and it's a hard balance for our chemists to come up with the right solutions. HFOs are less flammable than hydrocarbons, but they still are mildly flammable. So they're going to have their own classification, which is the A2L. HFO refrigerants contain fluorine, making them less flammable than hydrocarbon refrigerants. The fluorine kind of tempers it a little bit. And that's one thing we have to talk about too. A lot of people don't understand that. R410A, that we know it is a mixture of 2 different refrigerants, 2 different chemicals. It is a 50-50 blend of R32 and R125. R32 is slightly flammable. So they mixed in R125 because it was a flame deterrent. So R410A is actually R32 and R125 mixed 50-50. And as we move into some of these new refrigerants, you're going to see a lot more like that R32. Most of the world uses R32. So don't be afraid of these new chemicals. Just need to understand where they come from. So when someone talks about R32, because companies like Daikin are going to be going to R32 in their package units here in just a couple of years, just be aware that it's not a horribly new refrigerant. It's half of the one that we already know, R410A. It just doesn't have the flame retardant in it. So HFO refrigerants, they are miscible with POE lubricants. That's pretty good. And one of the most common ones is R1234YF. It is an HFO refrigerant currently being used in chillers. And if you didn't know, R134A in the automotive industry, because it has a significant fluorine level, was chopped off the block completely. Cut it off, 2015 United States. So if you have a vehicle manufactured in the United States that's not a commercial vehicle, 2015 and above, you don't have 134A in your vehicle anymore. You have R1234YF. Most people don't understand that. We chopped R134A out of the automotive industry because of its fluorine. Didn't really talk about it, did we? Anybody you ever see any commercials that said new and improved? Remember when R410A came out? New and improved, Puron. We didn't do that with R1234. We just went, hey, Ixnay with the 134. So we're going to see a lot in our industry, I'm afraid. We're going to see regulations affecting our refrigerant faster than we have the opportunity to say anything about it. So, you know, on all of our programs, that's all we do is we try to prep you for what is changing in our industry and make you aware of it. So when you encounter it, you're not afraid of it. If you are used to working on your vehicle and you go out to work on your 2015 or newer vehicle, and you pop the hood and you got your R134A gauges and you go, wait a minute, something's different. Now, you betcha. It's been different for a few years. You just weren't aware of it. So lots of changes in our industry. If you've been to a two-door pop cooler at a checkout lane at a grocery store near you, that doesn't have R134A in it. It has R290. Hydrocarbon refrigerants are an elementary compound of hydrogen and carbon. Although flammable, these refrigerants have the least amount of danger to the environment. Hydrocarbon refrigerants have no ozone depleting potential. That's cool, no chlorine, and a very small effect on global warming, like really, really small fluorine level. So the GWP values less than 10, very, very low on R600 and R290. R290 is currently the replacement choice of R134A in small fractional systems. We'll talk about that a little bit. We can't use a whole lot of it. Why? It's flammable. Nobody wants 4 pounds of propane in their air conditioning system, do they? Oh, that's right, California does. Some hydrocarbon refrigerants are considered natural refrigerants, right? Like propane, very natural. We just have to filter it. Propane cylinders for grilling should never be used as a refrigerant as they contain impurities. You know, we add sulfur to those so we can smell it. So propane in its purest has no odor to it. So our R290 propane, I'm at home, I'm not at the shop. If I was at the shop, I'd actually show you. We carry 1 pound cans of R290 here at Johnstone Supply. It's purified propane, it has no impurities in it, and it does not smell. So one of the dangers of some of these HC refrigerants is that they don't have an odor to them. If I have a leak on an R290 system, I don't smell it. It's not like the propane in our grill. We have a couple different types of refrigerants. So I want to talk about azeotropic and non-azeotropic mixtures. So an azeotropic refrigerant mixture contains 2 or more refrigerants, right? So if we look at a chemist, they're trying to balance all of these different chemicals so that we can have a safer chemical. So we're going to have all sorts of new chemicals out there because chemists are going, hey, let's mix these things together and let's find the safest ones. So with an azeotropic refrigerant, at a certain pressure, an azeotropic mixture evaporates and condenses at a constant temperature. So that just means I can take different chemicals, pour them all together, and they act like one chemical. That's it. So it acts like a single component over its entire range. So an azeotropic mixture acts like one mixture. So no matter what temperature it's at, or whatever pressure, they correlate exactly. We have another one, though, because not all chemicals like each other. So if we talk about zeotropic or non-azeotropic, the refrigerant mixture are mixtures of components that have different boiling points. And it's a mixture of a blend of different refrigerants. So the blend may be binary, which means it has 2 parts, or ternary, which means it has 3 parts to it. If we look at R410A, R410A is a binary, and it does not have a perfect glide to it. We call it near azeotropic. There's actually about a half a degree or so. So even though we've got 2 different chemicals in R410A, they don't like each other perfectly. They have about a half a degree difference on them because that R32 and that R125, they boil at about a half a degree different. So there's a slight difference. When we first came out with R410A, manufacturers were very afraid of this. They, when we first started having warranty evaporator coils, a lot of manufacturers give you a refrigerant allowance because they wanted you to pull all that refrigerant out, because I might be able to lose. If I was in 1/2 a degree from that boiling point, I could lose one of those chemicals, not the other. And we'll talk about that here in just a second. So what happens is when we have a blended refrigerant, blended refrigerants are normally associated with having what is called a temperature glide, which means they don't act exactly the same together. It's due to the blended parts having different pressures for their saturation temperature, right? If I have, like, I can take some of them, like a temperature glide can range a few tenths of a degree, like R410A, 5/10 of a degree, to 12 degrees or more. And that gets a little bit scary, because what that means is if I'm used to using my temperature pressure chart, I'm used to looking at my gauges. If I went to, my chart that I had earlier at 268 or something like that, PSI for that refrigerant, it was like 22 degrees or something. Anyhow, if I look at my chart, I know exactly at this pressure, my refrigerant is boiling at this temperature, right? That's easy to calculate my superheat and subcool because it's right there. Well, if I have a blended refrigerant, I may have a window. And when in the commercial world, when we moved from R12 and we were taking R12 out, one of the interim refrigerants we had was R414B. Some of us know it as Hot Shot. Hot Shot had a glide to it, which means this. It had a bubble point and a dew point based on its 2 different refrigerants. So if I would put my gauges on there, and I say maybe I looked at my gauges and I went, okay, R414, actually, instead of it having an exact temperature here, I looked on my chart and it had this glide, this other color on my chart. And I went, well, what is that other color? And it said, well, it's not an exact temperature now. It's going to be a temperature here because of this refrigerant, and it's going to be a temperature here of this refrigerant. So it's basically telling me that at one point, at one refrigerant, I will condense here, and at this one, I will condense here. But in between, I can have a mixture. One refrigerant can be vapor, and the other one is probably still liquid. So I had a window now of my boiling point. It wasn't an exact number. It was, hey, one of your chemicals is going to start boiling here, and the other one is not until I get down to here. So I open up a window, and it changes the characteristic of that refrigerant quite a bit. And as we see some of these new refrigerants out, you're going to start seeing more about bubble point and dew point. We haven't heard about it in a long time, since the 1990s when we were starting to do interim refrigerants. Once we went over to R410A, we kind of said, nah, we don't really need that. It's only half a degree. We're not going to worry about that much. But some of these new refrigerants we're going to see, you might start seeing this. And one of the effects that you have on it, if I had an R12 cooler and I was running it on a pressure control instead of a thermostat, my R12, I knew that at 40 degrees, my R12 was right here, right? Well, when I took out my R12 and I put in R14, instead of it being there, it was there. So my pressure control couldn't keep my temperature right at 40 degrees anymore. It would swing it. Because I had like a 6-degree glide, that means I had a 6-degree temperature glide. So instead of it staying right at 40 degrees, I might run down to 37, and I might go all the way up to 43. And the customer will go, hey, my cooler used to keep 40 degrees all the time. Now it's 37 and 43. It's all over the place. And I go, yeah, that's because of that new refrigerant. That new refrigerant has a window in it. And they're like, I don't care, put the old stuff back in. And you go, I can't. It's gone. So don't be surprised when we start having those kind of scenarios in our industry. So it's good to brush up on this stuff. So Z-tropic and some near azeotropic blends use bubble and dew point to indicate the condensing and evaporating temperatures. They're there, they're just at a little bit different place. So bubble point, that's kind of the liquid. The values are used when calculating condenser subcooling. Because remember, on a condenser, I just want to make sure I'm all the way liquid. So when I have a window, I know, hey, yeah, my top one's liquid, but my other chemical says, hey, I ain't liquid yet. You got to wait till I'm down to liquid. So it makes that window there. The dew point, same kind of thing. So it's going to be used for superheat. That's going to be on our evaporator, because one chemical is going to say, hey, I've already boiled off. And the other one says, sorry, sucker, I got 4 more degrees before I start boiling. So it makes a window that thing is actually going to boil. So dew point and bubble point are going to be more common in our industry than what you're used to right now. R400 series refrigerants, R410A, R404, 407, 422, they are near azeotropic blends, blends that can leak from a system at uneven rates due to different vapor pressures, which can affect the percentage of each refrigerant. You know, the proper charging for any R400 refrigerant is to weigh the refrigerant in on the high side with liquid. We don't put it in as vapor. That's why when we're charging with R410A, we put our tank upside down, right? Because we want to make sure it's all liquid. That wasn't always necessarily so, because if we had like an R22, we didn't worry about it. R22, if I had it upright, I just had R22 vapor on top, right? And R22 liquid in the bottom. R410A, depending on the temperature of my tank, I could have maybe more of my R125 in vapor form than what my R32 is. My tank may be a perfect blend, 50-50, but my vapor might not, because they boiled at different temperatures. So we have to put it in as all liquid on any 400 series refrigerant. So what that means is, if we look at that, let's just take, imagine we were looking at this as R410A, right? Which kind of is, actually. You have different fractionization of the refrigerants, which means that if I have a leak at a certain temperature, I could actually leak more of one refrigerant than the other. So R407C, that has a very high temperature glide, right? So let's look at R407C instead of R410. So R407C, it's a blended refrigerant. It's got a couple of refrigerants in it, right? So when it's in its liquid stage, it's 2 chemicals that are equal, balanced, right? So in liquid form, it acts as one liquid. When it boils, because remember, they boil at different temperatures, when they boil, I could have a change in my refrigerant. So if I look at that thing and I went, okay, so now this is just for, I don't know exactly what this temperature would be because I don't know what my pressure is, but let's just say at whatever pressure my system is, my R407C is in liquid form. Let's just say 40 degrees. And let's just say at this pressure, whatever pressure we are at 40 degrees, one of our chemicals begins to boil before the other one. So let's just say chemical A, we'll use chemical A boils off at 40, and chemical B doesn't boil off until 42. And my temperature on my tank is 41 degrees. So it's sitting in my van. It's 41 degrees outside. In liquid form, all of my liquid is 50% chemical A and 50% chemical B. But at 41 degrees, as soon as I got above 40, chemical A started boiling into vapor. Chemical B did not. So I started getting more of chemical A. And so then I rose to just below 42 degrees, 41.8. Chemical B hadn't started boiling yet. And chemical A had already been boiling for another degree, a little over a degree. What ends up happening is that vapor that's in the top of my cylinder now has the potential to be 75% of chemical A and only 25% of chemical B because it hasn't boiled off. My liquid's still the same. I still have a pretty even level of 50-50 liquid, but because they started boiling off a little bit different, I could have more of chemical A than chemical B. And that is what we consider fractionization. What if this was an evaporator coil running at 41.8 degrees? That's pretty realistic, right? If I had a leak, if this was an evaporator coil and I had a leak at the top or at the outlet of my evaporator coil, over time, running at 41.8, I could leak all of chemical A and almost none of chemical B. So my 407C, ends up not even being a 50% mixture anymore. It changes very, very drastically. So it's something to be aware of. We were scared of that when R410A came out, and then we found that it was only half a degree. It wasn't a big deal. But 407C, you betcha. You have a leak on R407, it doesn't matter the size of the leak. All of that liquid comes out, and you put all new liquid back in when you're done repairing. Even though the pressure temperature chart relationship and operating characteristics may be almost the same, the refrigerants cannot be interchanged. So I can't take out an R22 and just slap an R407 without looking to see that it's operating the same. I can't take a half of a 40. I can't take a low R22 system and dump 407 on top of it because I'm making a new chemical composition, right? So although the saturation pressure temperatures behave similar, the potential refrigerants can do damage. They can, oxidize copper tubing, all sorts of characteristics. Whenever you start blending refrigerants, you become a new chemist, and I don't know that any of us are qualified to know what that chemical is. So due to the flammability of some hydrocarbons and HFOs, the equipment must be designed to handle the refrigerant. Therefore, EPA regulates the maximum amount of refrigerant that can be used in the new systems by their type and by their use. So that R290 that's being used in those coolers is just a few ounces. It's actually measured, it's in grams. I don't know if we'll get into that. That might be a separate class. When retrofitting or converting a system to use a different refrigerant, only EPA approved substitute refrigerants can be used. Remember, EPA does not approve any substitute refrigerants as direct drop-in replacements to service an R22 or any other system. So EPA doesn't say that. EPA is just teaching you what proper refrigerant procedures are. A lot of our chemical manufacturers are going to be the ones that's going to dictate what are the best refrigerants. So we have low, medium, high, and very high pressure systems. To better define leak rates and service recovery levels, the EPA lists refrigerants in 4 liquid phase pressure ranges at a 105-degree condensing temperature. So if I have 4 operating systems all operating at the same day, and all of those are running about 104-degree condensing temperature, then I'm going to have different characteristics of different refrigerant system. So let's look at some of those real quick. So there'll be our different classifications. If we look at low pressure refrigerants, they have a pressure of 30 psi or lower at a liquid phase temperature of 104 degrees. So those are some of our lower temperature stuff, lower pressure stuff like R11, R123, R245, and one of the newer ones, HFO 1233. So HFO 1233 is going to be a low pressure. It's going to do some replacement for some of these commercial chillers and such. If we look at medium pressure applications, they have a pressure between 30 and 155 at a liquid phase temperature with a 105-degree condenser. So that's going to be like R12, 124, 49, 134A, 600, 1234YF, and that 1234ZE. So they're considered medium pressure systems. If we look at high pressure systems, a lot of us are going to be familiar with this. Those are systems that have a pressure between 155 and 340. So their head pressure is going to be between 155 and 340 when it has a condenser temperature of 104 degrees. So that's most of the refrigerants we know. R22, R404, 407, 422B, 422D, R410A, 441, and 717. So what we work on in residential HVAC is considered a high pressure application. We do have now a very high pressure class of refrigerants. They have high side pressures over 340 degrees when I have a condenser that's at 104 degrees. The main one, and we'll talk about it some more, is CO2. CO2 is classified as R744. We have different oils in our systems. Most HFC or HCFC refrigerants and ternary blends use synthetic alkyl benzene. We used to use a lot of alkyl benzene oil in our systems, especially with our reciprocating compressors. When retrofitting HCFC equipped refrigerants systems to HFC refrigerants, or when working with newly manufactured systems, synthetic polyester oil is most commonly used. So most of us are familiar with POE, polyester oil. Ester-based oils cannot mix with any other type of oil. So that's the thing we have to be careful with. Sometimes when we change refrigerants, we actually have to change oil as well, depending on what our operating system is. So when we talk about retrofitting systems, before retrofitting an HCFC system to an HFC refrigerant, the other types of oils must be removed from the system before adding the ester base. And I did that a lot in my commercial industrial rack systems. So if I had, say I had a commercial medium temp system that was operating on R22, when I took that R22 out, it probably had an alkyl benzene style oil. We had to actually drain all the oil out of that entire system. Had to go through and replace all the O-rings and put new polyester oil in it to be able to go to a new refrigerant. So it can be very time consuming to retrofit a system with a new refrigerant. Care must be taken when using ester-based oils. They are very hygroscopic and will absorb moisture out of the air and through some containers. So polyester oil, if I take me a can of nice clear polyester oil, open up my can, take my safety device off from it, I put it into a container that looks pretty clear, might have a little tint of yellow to it, and I put it on the table. If I have a fairly humid room and I come back tomorrow, it's actually going to be higher level inside of that, and it's going to be milky because it has actually absorbed moisture from the air. So our 410A that we use, it uses POE oil. So we have to be aware that these POE oils are quite hygroscopic. And we actually have manufacturers like Daikin moving into newer style oils, trying to get away from some of that. A part of doing and understanding refrigerant management is understanding where we came from. So a lot of this was brought to us through the Montreal Protocol and the Clean Air Act. So there's going to be some questions on this, and they want you to understand the history of where we came from. So the United States is part of the Montreal Protocol, which is an international treaty that addresses ozone depleting substances. So it's not just the refrigerants that we know, it's a variety of different substances that are that use manufactured chlorine, right? Because that chlorine is our culprit. So we are a part of the Montreal Protocol, and as part of that, what they decided was when they met for this, we'll talk about the date here in a minute, when they met for this, they decided that we had to make a change to our refrigerants because we knew, scientifically proven that our refrigerants was a major culprit in the change of the world that we live in. So to stop the damage to the stratospheric ozone layer, the United States is phasing out or has already phased out the use of all chlorofluorocarbons, hydrochlorofluorocarbons, and any other refrigerants that are harmful to the environment. Harmful to the environment. So it's based on the chemical composition. We started with chlorine, but we're now moving into the fluorinated ones. So if we look at that, Section 608 of the Clean Air Act, so that's a portion of the regulation that we use, which that is what governs our license. This is where our license comes from, right here. So Section 608 of the Clean Air Act sets forth the rules and regulations for refrigerant handling in the HVACR industry, us. There is a Section 609, and it pertains to automotive. Paul Grimm, master technician here with the 609. So he's carrying a 608 and a 609. They're two different certifications, but it's for the same thing. It's for safe refrigerant handling. We are the HVACR industry, and we are governed by Section 608. So Section 608 certification allows a technician to purchase or handle regulated refrigerants. You cannot come into a Johnstone Supply and buy a jug of refrigerant without a 608 license. So distributors that sell HCFC, HFC, or other regulated refrigerants must verify the purchaser is or employs a Section 608 certified technician. So that is our responsibility. We actually keep your certification number on file at Johnstone's under your name. So anyone performing an activity that violates the refrigerant circuit, including removal of refrigerant or replacing a component containing a regulated refrigerant, must be certified at the proper level and have the type of recovery equipment that is required for that section. And as we dive into type 1, type 2, and type 3, we'll go over all of those individually. So, it is illegal to knowingly release CFC refrigerants, HCFC refrigerants, or HFC refrigerants during the service, maintenance, repair, or disposal of appliances. A technician must have their Section 608 certification card in their possession when performing an activity regulated by the Section 608. If your 608 certification card is lost, request a replacement from your certifying organization, not the EPA. The EPA does not, they govern it, they don't issue it. That's where companies like ESCO, who provides this fantastic presentation, come into play. They are the educational body and the governing body of the license. The EPA just sets the requirements. A person is not required to be a Section 608 certified technician when servicing an external electric circuit or sections of the system that do not involve the refrigerant components. So you can be an apprentice and you can help service that AC unit. You can do electrical diagnosis, but if you put those gauges on that thing, you better be certified. Because if an EPA inspector comes by and asks for your card and you don't have it, somebody's getting a nasty fine. The Clean Air Act, so that is part of the EPA regulation, allows for releasing an exempt refrigerant like ammonia or CO2, or a small amount of refrigerant mixed with nitrogen, like when we test charge systems for leak detection. Otherwise, they don't allow it. As of 2017, look at this. As of 2017, a technician, not the company, the technician can be fined $44,539 per day per violation for violating the Clean Air Act, including knowingly releasing non-exempt refrigerants from appliances. So pretty significant fines available. So these are, these are the regulations that, support the necessity for a 608 license. Service technicians who violate the Clean Air Act provisions may lose their certification in addition to paying fines and be required to appear in court. It's taking this stuff very seriously. It's the technician's responsibility to comply with any future changes in the law or EPA regulations after a technician becomes certified. That's why I've been encouraging everyone to join this program, even if you're already certified, because there are a lot of changes that are happening in our regulations, and it is the technician's responsibility to stay up to date. It's not like a lot of state licenses that require continuing education hours. Your EPA, it's a voluntary education process. And so we highly encourage you to stay educated with new rules and regulations. State and local governments may establish laws that contain stricter requirements than the Clean Air Act. So, local municipalities can enact more stringent regulations if they want to. What this is just saying is this is the minimum expectations. So the phase out for the production and import of newly manufactured R22 and HCFC 142B will be in year 2020. We all know that. R22 is out the door. After the phase out of HCFC refrigerants in 2030, that's all, look at that, all HCFC refrigerants in 2030, supply of those refrigerants for equipment servicing will come from recovered and reclaimed gases only. It's all HCFCs. It is not a violation of the refrigerant management regulations under the Clean Air Act to service a system that uses CFCs or HCFCs after the phase out of those. Right, reclaimed refrigerant must meet AHRI standards. Remember, we get into AHRI, we're talking about health and safety, before it can be resold under EPA's regulations. Very strict requirements. We'll talk about that in a minute too. Technicians can only use CFC, HCFC, or HFC refrigerants back into the same appliance or into another appliance owned by the same owner. So if you have an apartment complex that owns a whole bunch of R22 systems and you have clean R22 coming out of a system because you're just upgrading to an R410A system or whatever, that R410A can actually be reused by that same owner. Can't be charged for it, but it can be reused by that same owner. It cannot go anywhere else and be used, but it can be used by that same owner. Used refrigerant may no longer meet the AHRI standards because it could have water, it could have moisture in it, it could have acid, it could have all kinds of contaminations. So it cannot change ownership without being reclaimed. When we also talk about some of the Clean Air Act stuff, Montreal Protocol, all CFC, HCFC, HFCs, and the HFOs, refrigerants recovery equipment must meet EPA standards. So recovery equipment must be tested according to AHRI standard 740. Good one to know. Recovery machines may be able to recover one or multiple types of refrigerants, and most of ours are. Now, some of our older recovery units, which we actually talked about in our recovery equipment class, some of our old ones actually used oil for the actual recovery process. And we had to change oil every time that we used those because we had different refrigerants, and some refrigerants didn't like the oils. So we had the potential to contaminate our equipment very easily. Desiccant humidifiers are not covered by EPA Section 608, and they do not, because they do not contain a refrigerant. Self-contained recovery devices remove refrigerant from an appliance without the assistance of components in the appliance. Now we're going to talk about some oddball stuff here, and it's going to apply primarily to type 1 and to type 3, type 1, type 3, not a lot for type 2, but you still need to be aware of it. We have two different types of recovery systems. So we have the self-contained, and we also have what we consider, what we work with the most. So recovery equipment that relies on the compressor in the appliance or the pressure of the refrigerant in the appliance is considered to be a self or system dependent. And a lot of people don't encounter these, but we need to be aware of what they actually do. And we'll spend a little bit more time on that here in a minute. So to make it easier to recover refrigerant, EPA regulations require appliances that do not have service valves to have a service aperture or a process stub. You'll find that on packaged window air conditioners, on domestic and fractional refrigeration systems. So that refrigerator that is in your house does not have service fittings on it. It has a process stub that comes off, which is just a piece of copper that's been pinched off and soldered, and that is it. You don't have service ports on that thing whatsoever. And you'll see that quite often in our type 1 equipment under 5 pounds. When disposing of appliances with 5 to 50 pounds of refrigerant, EPA does not require technicians or the company employing the technician to record the model and serial of the appliance. However, records must be kept that include the type of refrigerant, the quantity of refrigerant and the type, the quantity recovered from disposed appliances in each calendar month, and quantity of refrigerant by type sent for reclaim or destruction. These are all new regulations that are going to be affecting our industry that people who have taken the EPA before last year probably not aware of. And we're going to be going over a lot more of these newer requirements on record keeping, because it's going to change our industry significantly. It shot down in 2019. 2020 is probably the year for all this stuff to be completely in effect. So EPA's refrigerant management regulations exempt certain refrigerants from the venting prohibition, right? Because remember, we can't vent a refrigerant except certain ones. And we'll learn about what those certain ones are. This can occur when and if the EPA determines that a certain refrigerant does not pose a threat to the environment if it is released. So some natural refrigerants, such as CO2, can be purchased by someone who is not Section 608 because it is just a natural refrigerant. One of the things is it's 9 o'clock. All right, thank you. It's probably going to go, it may go a little bit over. So just hang in tight, everyone, and I'll get through just a little bit more and we'll finish up tomorrow. Actually, yeah, let me get through a couple more slides. It is lawful to service existing R22 systems and use existing supplies of R22. It is not legal to top off an R22 charge with another refrigerant, such as an R410A or any other refrigerant. Topping off of one type of refrigerant with another can void equipment warranty, ruin the refrigerant, damage the equipment, and cause severe personal injury or even death. So when discarding or disposing cylinders of CFC refrigerants, HCFC refrigerants, HFCs or HFOs, recover all remaining refrigerant, render the cylinders useless, and recycle the metal. Sounds like a great place to stop, doesn't it? Lots and lots and lots and lots of information on this. And there's so much stuff to cover. And that's why even an entire week of doing one to 1.5 hour classes is going to be tough to cover everything. So there is a lot of effort that you can do on your part. You can purchase the study manual. I should have this back up on our channel so you can do some revisiting of what we've been discussing today. You've got all of the free practice tests at esco.com, and just do some due diligence for yourself. Invest in yourself. I keep preaching this to everyone. Right now is the perfect time to invest in yourself. And here at Johnstone Supply, that's what we've been doing. We've been providing free education, temporarily free education, to build yourself and to make yourself more of an asset for when we go back to our industry. So I appreciate everybody hanging on with us for 1.5 hours, and look forward to regrouping tomorrow, and I'll see you all at 7:30 tomorrow. Everybody have a good day.